Hi everybody, another video today. We're going to talk about antiderivatives. Again, I know you can do the computation, you need to practice the computation. That's not the point of these videos. I really want you to understand the ideas. The ideas are the things that we expand upon and we use in our careers, and we apply the ideas and the concepts in order to solve problems that have yet to be solved. So let's talk about antiderivatives and the whole concept associated with antiderivatives. So really, antidifferentiation is a function. That's why I put the factory in here. You know that I have this desire to use the factory idea for functions, and that's what I'm doing here. So what we're going to do is we're going to put in a function into the factory. It is going to calculate the antiderivative, and it's going to give me a function out. So we have functions in, functions out. The relationship is if I take the output and I differentiate it, I will get the input function back. That's the whole idea. So it's as simple as the following. I'm going to put in the function 2x, and what I'm going to get out for antidifferentiation is x squared. Why? Because if I take the output, if I take the output function x squared and I differentiate with respect to x, I get 2x, which is what I get over here. Now it's a little bit more subtle than that. And the reason that it's a little bit more subtle is because in reality, I could differentiate x squared plus any constant, and I would still get 2x. So this is an interesting and important attribute which we'll expand on in the next couple of weeks associated with antiderivatives. Anytime I take the antiderivative, I'm always going to end up with plus some constant. Because when I differentiate that function on the output side and I differentiate it, the constant will become 0. So it doesn't matter what that constant is. The antiderivative 2x, when I push it through the factory, it will work for x squared plus 1. It would work for x squared plus 3. It would work for x squared minus 7. Those are all my functions that if I differentiate them give me 2x. So 2x is the derivative of all these functions, which means each of these is an antiderivative for 2x. Let's take a look at a couple more examples. So let's say that I put sine of x in here into my antiderivative machine. So I have the antiderivative, I'm going to calculate it, and the question is what function when I differentiate it gives me sine of x? And the answer is negative cosine of x. Except it's negative cosine of x plus any constant. When I differentiate, that constant's going to be 0. That's the antiderivative. This is the whole concept. It's just a very straightforward idea. It is reverse differentiation, if you will. I'm not going to use the word inverse right now. That's not really correct, but just think of it as the reverse of differentiation. So here's kind of the confusing part. The notation that we use is not a factory. It's not a big A. We don't say, what is the antiderivative of sine of x is equal to negative cosine of x plus some constant. We don't do that. We use the following symbol. We use the integral of sine of x dx is equal to negative cosine of x plus c. So the notation we use is the integral sign and this differential. Why? How could that be? That's what I want to explain to you. I think it's a little bit backwards for us to talk about antiderivatives before we talk about how this whole thing came about. Because it turns out that these two symbols actually have meaning with respect to where they originated from. Let me give you another example. All right, let's say that I have a piece of property here, and it's got straight borders on the east and west and on the southern side. But the northern side is defined by a river. And what I want to do is I want to figure out how much acreage do I actually have. I can't use a simple formula like I do for a rectangle or a circle or something like that, because I have this strange shaped river, which isn't necessarily something that I know anything about. But what I could do is, and you would think of this pretty quickly, is I could start to chop up this into small rectangles, and I could use these small rectangles, and I'm going to chop it up into 8 rectangles. I could use these rectangles as a means of approximating. So I could chop it up like this, and I could conveniently think about the fact that I have these 8, and what I'm going to do is I'm going to take these areas here and just add them up. And of course I'll have a little bit over and a little bit under as I go around, and I could just add all of these up, something like this. And if I wanted a higher resolution on my accuracy, I could take more rectangles. So the whole idea here is that I'm going to sum up however many rectangles I have. I'm going to say the sum, that sigma, right, is the summation. Summation I going from 1 to n of, I have all these rectangles. Rectangle 1, rectangle 2, rectangle 3, up to rectangle n. And each one of the rectangles has a height and a width. And when I sum those together, I'll have approximately my area. Okay? I'll have approximately my area. And as we discussed, the higher the number n, the smaller I keep cutting these rectangles, the more accurate my approximation is going to be. Let's stop for a second. Let us take this and put on a coordinate axis system. So I'm going to put on a coordinate axis. This is going to be x, and this is going to be f of x. And I'm going to define the function to be this blue right here. Right? This is a graph of my function is in blue. And what I'm going to do then is I'm going to take from a to b is my function. So I have some interval, and I'm going to call the function f of x. So I have f of x, which is really the river, on some interval a to b. And what I'm going to do is I'm going to look at the height of each of these, right? So here, let me chop this up and call this x1, and call this point x2, and call this point x3, all the way over here to b, which is the same as x capital N. And at each one of these I have a height, and that height is f of x1, and then I have a height here, that height is f of x2, etc., until I have a height over here. That height right there, right, this distance here is f of x5. Right? Every one of these is a height times this width. Well, what I have is I have a sum now, I equals 1 to n, same idea, but now I have my function f evaluated at all of the different x sub i's, because I've taken my interval and chopped it up. And I'm multiplying by the distance between x sub i's, which I'm going to call delta x. So I'm going to call this distance here delta x. And so every space in between, those are all delta x. So every rectangle has width delta x. So this piece here is the height h, and this is the width w. So now for any function that you give me, not just the river, but any function that you want to give me, I have a means of calculating area. I have a means of calculating this area under the curve, or in the case of my property, between the bottom property line and the river. I can calculate all the area that I have. So as we discussed, the way that I make this more accurate is by taking more and more and more rectangles. Notice that this is equal to, and let me just write this down. So this is an equivalent way of writing it. So delta x is really b minus a divided by n. It's the total interval here divided by the number of chops that I've put into it. And again, I'm keeping them equally spaced. I don't need to do that, but as you're going to see, I can do that. It doesn't make any difference. So this is really the delta x. Well, now I'm going to apply the idea of calculus. What have we been doing since week 1? Taking limits. We know it's more accurate when we take more and more and more rectangles. Let's take the limit as we go to infinity. So what we're going to do is we're going to consider the limit as n goes to infinity of this summation. I equals 1 to n, and then I have my f of x, I, and b minus a over n, and remember this is delta x. Well, I don't know what that's going to give me, but what it ends up generating is antiderivatives. And it's integration. That's really where we're going with this. I just want to show you where the notation comes from. As we take this limit, we can see that this thing is going to infinity, but that's multiplied times some individual heights, and I'm adding them all together. We'll talk about calculating this limit later. That's really more of a topic for the next course. But where this ends up going is this summation sign becomes the integral sign, and the delta x becomes dx. The delta x shrinks down and approaches 0. That's what dx is. And the integral sign is literally the summation sign. It is the capital sigma, and it's been elongated, and it stands for summation. And what I am doing when I integrate is I am summing the function f, which are a bunch of heights, times a bunch of widths, and I'm adding them all together. It's just that the width is going down towards 0, so this becomes a conceptual thing. But this, and I'm summing from a to b. This is a number. This is called a definite integral, but it's directly related to antidifferentiation, which is why this notation is used. It's the reason that I have an integral sign, which is just a summation sign, that's what it stands for, and a dx, which is just a delta x. It's exactly the same idea. The fundamental theorem of calculus takes these two ideas and marries them together. We'll talk more about that later. I just want you to understand why we're not using a big A for antidifferentiation. We're using an integral and a dx. And the reason is because integration is just summation of the function multiplied times a bunch of vanishingly small widths. That's it. Good luck with the homework.